everyone. Thanks for joining us. We have an exciting webinar today. Good morning to those joining us from Europe. Good evening to those joining us from Australia and Southeast Asia, and a huge shout out to anyone staying up late to watch this in North and South America. So yeah, I said we'll have a very exciting webinar today, which I think is a glimpse of the future, and that is the integration of cheminformatics and chemical regulation, as well as the integration of cheminformatics and hazard and risk assessment. And we have some excellent speakers, and also we're going to have some demonstrations. My name is Hans-Peter from the Norwegian Geotechnical Institute, as well as the Norwegian University of Science and Technology, where I coordinate the ZeroPM project, which stands for Zero Pollution of Persistence and Mobile Substances. And this webinar is part of our Science Policy webinar series. And I'm joined in hosting this webinar by my colleague from ZeroPM and EMPA in Switzerland, Xianyun Wang, who will introduce our speakers. Before he does, I just want to say some general house rules is that everybody attending is encouraged to use the Q&A option below at any time. So you can do this live because it's possible for the speakers to answer the questions if they're not, of course, speaking. And then at the end of the webinar, we will open up to a Q&A session where I will read some of your questions and we can have some dialogue with the speakers about them. So I have to say I am very excited about this webinar, and then I will hand it over to Xianyun to introduce the speakers. Xianyun.
Yeah, many thanks, Hans-Peter. Yeah, it's my great honor to introduce my long-term collaborator, Glen Walker. I think I've got to know Glen when we were doing the global chemical inventory, and it has been such a joy with such a great thinker. I think Glen is a chemist by training. He has worked for the Australian Government Department of Climate Change, Energy and the Environment and Water for the past 16 years. Leading work on the environmental risk assessment of chemicals. He collaborates with national and international researchers working on new approaches to the environmental assessment of chemicals and pollutants. So his team is currently developing new regulatory informatic tools and to inform the chemical substitution and assessments. So it's really exciting to have Glen and Daniel here. Daniel is the main man behind the ARChIE, the cheminformatic tools that Glen and his team developed. So I was really excited. I'm really excited. And without further ado, I would give the floor to Glen.
Thanks, Xianyun, and thanks Hans-Peter and Sarah Hale for the opportunity to speak today. And I'd like to also wish everyone a good evening, a good morning, a good afternoon, wherever you are in the world. As you can see from the window behind me, it's late afternoon here in Australia. So as Xianyun was saying, I work for the Australian government in the general area of environmental risk assessment. And I lead a team that's working on next generation prioritization approaches and informed chemical substitution. I'll be making a short handover shortly to my colleague, Dr. Daniel Weber, who's been working in my team on on prioritization frameworks generally. But what we'll be talking about today is a very successful and to some extent unexpectedly successful development from his program, which is the what we're calling the Australian Regulatory Chemical Informatics Engine. So without further delay, Daniel, could we go to the first slide? It's customary in Australia, we'll just go back to that acknowledgement of countries, to acknowledge the First Nations people in our country, and particularly where we live and work. Here it is the Ngunnawal and Ngambri people, where both Daniel and I have been based, and we take the opportunity to recognise the elders, past, present and emerging, of those two peoples, and recognise their continuing connection to the country that we live and work on. So next slide, please, Daniel. So as I said, the work that we do emerges from the general area of environmental risk assessment of chemicals. And those of you on the line will appreciate that this has a very wide scope and scale. It encompasses the range from individual species through populations, all the way through ecosystems, and all the way ultimately to major environmental compartments like the atmosphere. So in the area of industrial chemicals, we may be interested in chemicals that enter waterways, but we may also be interested in chemicals which enter the atmosphere and affect global warming and the ozone layer through ozone depletion. Next slide, please, Daniel. So one of the other aspects of chemicals regulation is the very wide scope and scale of chemistries, particularly in industrial chemistry, industrial chemicals, that is required to achieve various functions, all the way from cosmetics through fuels to lubricants to plastics. The scope and scale and diversity of chemicals is simply astonishing. Next slide, please, Daniel. Here I've represented a small snapshot, about 1% of the Australian inventory of industrial chemicals, which is a mid-range inventory of around 40,000 chemicals. So now we begin to see the scope and scale of the challenge that regulatory scientists and chemical risk assessors and chemicals risk managers face in terms of the scope of impact of chemicals and the scope and diversity of chemicals that are used very widely in our economy. So Daniel, if we could go to the next slide, please. So we've talked about our inventory is around 40,000 substances. So that is the origin point for risk management within Australia, those 40,000 chemicals listed on our inventory. But in the work that Jean-Yun alluded to, that he led 2 or 3 years ago, was to look at the global inventory of chemicals, where the true number is around 350,000 substances. And when you take that perspective, with chemicals being a globally interconnected industry, the true scale of the problem that we confront is more along the lines of 350,000 substances. So it's a very large number of substances, a very wide diversity of chemicals, and a very wide range of potential impacts on the environment, all of which has to be integrated if you are trying to manage in an organized, scientifically driven way, the way that chemicals are impacting the environment, and ways to reduce those risks through sound management practices. All of that means that we need to be able to efficiently harness, compare, and analyze information to prioritize our efforts. If we don't prioritize, we're not going to make progress. And that has really been the thrust of our efforts over the last 10 to 15 years, to try and prioritize where we do the assessment and what level and depth of assessment that we carry out. Because resources are finite, we need a way to prioritize efficiently and effectively. And here I would say Australia, like other countries, has been going through a prioritization process for its large inventories that have been in operation for several decades. So we're not unique in this. We face very many of the same problems that our global peers do, but our approach has some, we hope, unique features. Daniel, could we have the next slide, please? So one of the key ways that we have been doing things is through chemical informatics. We've been developing decision support tools within the general space of chemical informatics for about the last 10 years. And here we've displayed the landing page of one of our more successful products, which we've published online on our GitHub site, which was the electronic chemical assessment tool. And as you might be able to make out there, it includes a relatively small subset of our inventory, around 3,000 chemicals. It provided us the first truly integrated multi-layer, multi-regulatory context decision support tool that provided us with a single platform to look at the hazards and risks of individual chemicals, and importantly, be able to compare those side by side. One of the great strengths of ECAT was that it allowed us to, for the first time, be able to integrate our available chemical information to do some very powerful grouping, which is at the heart of modern prioritization practice, both in Australia and globally. So this is just a bit of a snapshot that the work that you're about to see that Daniel has led on comes out of a matrix where we have been developing chemical informatics as a core part of our approach to next generation prioritization, and also to making the best use of the available information for chemicals risk assessment. So with that, I'll hand over to Daniel, and now you'll see all of the work that he's done in the last very productive 12 months. Over to you, Daniel.
Thank you, Glenn. So I'll start off with just describing the journey that really led to me eventually developing ARChIE as it stands. It all started off with just being asked a simple task of, we've got 40,000 chemicals on our inventory. We need to prioritize these. And the first question I asked at the time is, for what? And that's how prioritization is purpose-driven. And at the start, it's for assessment. And a key part about this is we're assessing because we don't know much about them. Our information is scarce, so we need to make decisions and prioritize chemicals based on information that we don't know. So you'll ask, what information do we have? Not much. And what information we do have is usually scattered across multiple different files and PDFs and Excel spreadsheets, and generally they're not really suitable for a screening type exercise. So what do you do? So the first response would be, okay, I'm a programmer. What I'll do is I'll write a Python script and I'll use my favorite Cheminformatics package. Cheminformatics is very important at this stage because you're trying to make it a predictive analysis. By querying substances directly or based on their chemical structure, you can really make the most of whatever scarce information you do. And using scripts allows you to really mine through all the scattered data sources and everything. But the issue with this approach is that you're faced with, okay, your boss goes, oh, Glenn asks you, oh, that's great. You got a list of priorities, can I run it myself? And the answer is no, you probably won't be able to install it. It took me forever to install this stuff on my computer. You'll take months just to try to run it. And then, okay, what was the algorithm? Well, you can't really explain that because it's all written in code. And, if you're the only programmer in the room, you're not really going to have much luck in making the whole process transparent. So, you don't really end up with many happy customers with this approach. And then going down the track, you'll be thrown another sudden issue, and there's this issue I'm presenting here is a circular economy issue. You have an article with hundreds of chemicals, and you'll find that you get presented a list of chemicals in this article that you want to recycle, and you're like, oh, I can't find half of these chemicals. And the reason why I can't find them is they're not in our inventory because they're imported articles and they're regulated differently to ones that are manufactured or imported just as a chemical or a product. So what you're faced with is this global inventory problem. So you're comparing, so you go, where are this? So your boss will give you all these lists and you'll be bombarded with lists. So, you're not working with a predictive exercise. You're trying to make decisions based on information you should have on hand that should be readily available. And it's also a list matching exercise. And my scripts that I just made before don't do this. So, now I've got to code up a bit of information code up a lot of stuff with a very little time. And that doesn't go anywhere very quickly. And not just annoying your boss, you're annoying your boss's boss as well, which isn't a very wise career move. So this led to me making ARChIE. And the reason why ARChIE is like, how do you make these advanced chemical analytics methods available to everyone throughout the regulatory environment? How do you make sure the information is accessible and at the fingertips ready for that next left field prioritization problem that you get? How do you introduce global context into the regulatory environment? And how do you facilitate how technical information is communicated between technical staff and scientific staff, as well as non-technical stakeholders that are usually the ones having to communicate your decisions to industry as well as the general public? And this is why ARChIE was invented. It was meant to be the central accessible platform that everyone can use. So I'm just going to jump straight into a demonstration just to show you what ARChIE is. So that should be coming up.
Yep, we can
so
see
ARChIE
it, Daniel.
Excellent, thank you. So ARChIE isn't really just a single program. It's a web-based application. It's actually consists of probably 6 to 8 different modules at the moment. So the first you greeted with just the landing page, and this highlights all the modules that are essential for either browsing, analyzing the data, or even importing the data into the system. So the first point that people will go to would be a navigator, and usually you just want to browse substance information. So ARChIE, you can browse ARChIE by substances. So right now we have 240,000 substances in ARChIE. Keep in mind that this is what the information you see here is mainly for development purposes. We haven't really prioritized making the information very complete or focused on the accuracy at the moment. So treat it with a grain of salt, but the information is good enough at the moment for the purposes here. But yeah, the first thing, you're greeted with 240,000 substances in a list view. As you scroll down, as each substance is listed, it'll also cross-check the multiple lists that are also deposited into ARChIE. So that'll be done on the fly, and we can get an immediate view of each substance's regulatory landscape. What inventory does it fall in? Is it under a hazard list? These are important things to keep in mind. We want to view by structures. We can index a different table of data, and we can look at the structures that are in ARChIE. So we've got 183,000 structures associated with those 240,000 substances in the database. So if you're interested in more information, there's different levels of ARChIE. So if you're interested in a substance, you'll go into its substance profile card or its substance profile view. And this is where it'll accumulate all the information in ARChIE throughout all its piles, and it'll put it into one location. And it's important to note that each substance can have multiple pieces of information. There's no limit to how many structures you can put to a substance. The chemical name, so these are being derived from PubChem or taken from PubChem here. 54 synonyms can be associated. There's no limit. So you can make sure everything's accessible, everything's searchable. But if you want to know even more about a piece of information, know where you got it, is it reliable? We can go into the metadata view, and it'll give you another rundown, a bit more information, like it's where was it sourced, where do we get it? Would we consider it official? If it's bad, do we inactivate it? Is it secured? Is it highly restricted information, and you might not be allowed to view it? So we have those bits. So so we've got a bit about the navigator and the prioritization and advanced search tool. A lot of these tools might be renamed in the future, so don't get too attached to them. This tool is where everything comes together. So this allows you to put together prioritization schemes and allows you to analyze the data in a customized and do-it-yourself fashion. So I'll demonstrate more about this later. There'll be plenty of demonstrations coming. But there's also the listing tool. So when we accumulate lists like the ACAS inventory, what we'll do is we'll upload into this listing tool, and this tool will extract all the identifiers like CAS-RNs, chemical names, EC numbers, any INCHIE keys, and it will basically map the substances that are in ARChIE to it, and it'll make a pool ready just to quickly scan as you browse information. So there's quick cross-checking that can happen, but you can also use these lists for filtering as well. So if you want to refine your analysis down into a particular list, you can do it that way. There are also some tools for data extraction and importing. So ARChIE has a very powerful data extraction utility that you can pretty much flood a whole database like I've got in less than a day, as well as there's some user management and system tools that I won't demonstrate here. I'm just going to switch back to the presentation. Oops. So I'll just recap on the design elements that I was keeping in mind when I was developing ARChIE. And the first thing is all about accessibility. So we went with a browser-based platform because everyone has a browser and can use it. So no one's required to install Python or any obscure packages that I like to use. It's also chemically aware. So this makes ARChIE very unique because not many chemical information databases allow you to query chemicals based on structure. And ARChIE has a lot of cheminformatics capabilities like structural similarity and substructure searching built in and integrated with every other conventional type of search and query you could do. We've also found it has to be intuitive. It has to be intuitive for technical people, scientific people, as well as non-technical people, because you're trying to use this system as a way of communicating your decision-making as well as information in very short time frames. It has to be extendable. So ARChIE is very modularized. So this breaks down ARChIE into manageable chunks that I can develop incrementally. It will probably never be fully, I'd say, complete, but it'll always be building. There's also data extraction, so high volume data extraction, as well as the ability to curate information in high volume is very important. So that you'll see a bit more soon about that. Also data integrity. It's also, when you're in a regulatory environment, you need to make sure that all the data you're presented with is fully traceable. You need to make sure you can go right back to the original source and be able to find it. But also there's some information that also needs to be secured. So there's that requirement. So we have to have this granularity to do that. And also has to meet end user needs. So this has all been designed next to the regulators as well as our risk assessors. So I've had constant feedback during these stages of development. Before I go on the demonstration, I'll just outline how ARChIE is structured under the hood. So ARChIE isn't just a big monolithic database. It's actually, it's an orchestration of several data tables that work together. So at the center of the database is just substances, and these are indexed by a substance ID, and these are attached to CASRNs, any identifier that gives this substance some meaning. All the information in ARChIE is collected in these special purpose entry tables, as I refer to them. And these entry tables and modules contain all the data, information, and analytical functions that are specific to a particular type of data. So if we're looking at cheminformatics screening, these are all contained in the chemical structure table. That'll have all the similarity searches built in, the substructure searches, as well as, it'll take all the SMILES codes and it'll automatically compute ARChIE keys and these type of identifiers and molecular weights and formulas within this module. Another layer, we have admin tables. So this is where all the metadata is managed for each data point. So this controls at fine scale, but per entry, it allows you to record about the source information, other general pieces of information. This is where you control the user authorization, who has access to these pieces of information, as well as present you with reliability descriptors. Do we consider this official in our regulatory context? No, is it a reliable study? This is where you'll put this information to. And in a separate table, we have what we call a substance list table. And this is really a user, a very flexible utility that allows you to just upload CSVs and Excel files, and it'll extract that information. It'll just make pools of substance IDs that will lump ARChIE into separate operating contexts, like our ACAS inventory or the REACH registered substances. This can all be done in this listing facility. So we'll do like another example. Do a work example of the problems that ARChIE can solve, and we'll start with, I'm interested. Let's just say hypothetical. I'm interested in what are all the persistent and mobile substances we have on the ACAS inventory. This is a bit of a problem because I don't have any persistence information in ARChIE just yet. But there is ZeroPM have released their initial list of 38 substances that they've assessed as persistent and mobile. So we can incorporate this list into ARChIE and screen against this. We also refine by our ACAS inventory, so that's an essential part of the analysis here. But an important thing to note is that the ZeroPM list was only an initial list. It wasn't meant to be complete. It's just to kick off the whole project. So we want to expand this and take out everything that's structurally similar to something on this ZeroPM list. And what we will get in the end is a list of substances that are on the ZeroPM list or have structural similarity. So we'll just run that demonstration and show how it looks like in ARChIE. So I've already compiled a bit of this. So in the prioritization tool, what we have done, we've actually assembled this the analysis I just showed in as a block by block format. So in this first block, we're going to filter by substance list, which is the ARChIE inventory. In the next block, we're going to then do an and go part of ZeroPM. And then we're going to do an expansion type of filter where we're going to anything that's structurally similar to this based on these fingerprinting and distance metrics. And we run that. So it's already been run. It'll take about 11 seconds to run. And we will visualize the results in. Okay. That's an unexpected problem. Well, you run it in the navigator. Sorry, I'll just run it again. Still ironing out a few bugs. And we'll visualize it in the navigator. So we've got 77. So we started with 38 substances on the ZeroPM list, and that blew it out to 77 just based on structural similarity. That's within our ARChIE inventory using that criteria. We can go back. We can then, if we want to, we don't like that view, we can actually just view directly by structures. So we can just change the table that we're going to assess it as. So instead of returning substances, we're going to return structures. And then we can just view the structures directly, and it'll give you a rundown of all the substances. And a lot of these are fairly much identical to the substances that were on ZeroPM, but they just have different names associated with them. So that gives us that view. So we'll just go back to the screen. So just to recap on what we just saw. So we saw two critical parts of ARChIE, and these are what we consider as vital analytical capabilities that are embedded into into the database. So the first one is we have what we call all-purpose prioritization filters. The idea of a building block approach that allows you to customize and do prioritization yourself. So this doesn't have to be done by me, it can be done by anybody, and they can do complicated cheminformatics just by using the prioritization tool. So it has a filtering capabilities. It also has a filter scoring capability, so I'll show that later, but you have the ability to attach a score to a filter and provide a ranked list of results, which is in essence prioritization. You can just rank only and don't do any filtering. And then there's also the concept of an expansion filter that allows you to make a predictive expansion of your list. So in this case, it was a structural similarity. And these predictive measures are all enabled by its built-in cheminformatics. And I always say this is implicit read across. You're embedding read across into your prioritization schemes. So first thing that you saw was something based on structural similarity. The idea of fingerprinting a substances and finding a distance and putting a number to that and filtering by that. ARChIE does support substructure queries as well. I won't demonstrate them here, but ARChIE does do it, and it's become quite important in our work. So, okay, so we'll just expand a bit more on this implicit read across functionality. We'll try to solve another problem with ARChIE. Okay, what is the most probable functional use of this substance? So with functional uses, I've taken most of these functional uses from the CP that the EPA releases, but this is by no means complete. So if I try to look for this substance in ARChIE, which I'll go to, I'll find I have no functional use information. But how can I infer functional use based on structural similarity? So what I'll do is I'll do a structural similarity search, and I will show our functional use tables and see if I can infer a functional use like that. So I'll go back to ARChIE. And so we'll go here. So this is the substance card of the information of the substance that I was looking at. If I go down to functional uses, no information. So okay, so I'll go to, okay, so now we'll go back to the prioritization tool, and then we'll do another screen. So we'll do a structural similarity filter. We'll put the SMILES code in. We'll use RDKit fingerprinting, a Tanimoto distance score, and any result greater than 0.7 score will be returned. And importantly, we're looking at the functional use table. We want to search functional uses. So we'll run it quickly. Oh, relatively quickly. And we'll go to the score. So we've got 3 substances that were produced with a similarity score of 1, and what we're listed is flame retardant. So now we can kind of infer just by similarity that this substance is probably a flame retardant based on similarity to another substance in ARChIE that was listed as a flame retardant. So we go onto this substance card. It's more or less the same substance, it just has a few more bromines attached to it. And if we go down here, we will see the functional uses here from CPDAT, and that's flame retardant there. So we'll go back to the presentation. All right, so to recap on a little bit, so I've shown that ARChIE is a centrally accessible system that our decision makers as well as our assessors can collaborate on. So everyone has access to this system. And in this scheme, what happens is the assessors are responsible for importing the data into ARChIE and maintaining the integrity of their sources and curating the information. And in real time, this curated information is delivered straight to our decision makers. So this is a constant process. We've also established that ARChIE has the ability to manage chemical information, but it also has the vital analytics built in. But I haven't really spoken about the global inventory aspect. So we're sure ARChIE has a lot of substances, but it's important that we can utilize this global context to solve what we consider cross-jurisdictional issues. Now, how could we deal with substances coming in? How can we look at this global inventory, which is actually a manifestation of tens to maybe 100 different sub-inventories and contexts. Now, how do we piece all this together and come up with a coherent story or coherent analysis to prioritize substances in this fashion? So we'll move on to the next, which would be the final demonstration of, let's just take our tire chemical, our circular economy problem that we had earlier, where we're presented with tire chemicals. So here we're going to have a list. So we've compiled a list just for our purposes of chemicals in tires that we've put together from literature sources mostly. And we're going to cross-check this. So we want to be able to identify what are the bad substances in tires. So what you'll go to first is probably the really bad list. So you go to the Stockholm and Rotterdam conventions first. So we'll compare those, because if there's any of these substances in there, it could be a little bit of an issue for recycling. But then we'll move on to other high hazard lists. So we consider the REACH Annex, the restrictions list and the REACH authorization list to be quite high hazard lists. So we'll tag those on. But just because something isn't listed doesn't mean it's not hazardous. So then we can use our structural similarity expansion filter to start to capture the substance that have been missed in this list, just so that we get those on our radar. And then we'll tag on another block, a filter block, and we'll also capture the REACH substance of very high concern candidates. So just because a substance hasn't been found hazardous yet, doesn't mean it won't be found hazardous shortly in the future. So we're going to want to capture these just so we don't make a decision prematurely. And then we'll return a bunch of several substances that are hazardous in title. But importantly, when they're coming through, we'll also score the list as they come through. So I'll put 15 points to these high hazard lists. We'll put 10 points to anything that's predicted based on these high hazard lists, and 5 points to the substance of very high concern list. So we'll do that demonstration. So what does that look like in ARChIE? So in the prioritization tool, we have the first substance list that initializes the filter set would be the chemicals and tires that we have already uploaded into ARChIE. We're going to compare it against the Stockholm and Rotterdam conventions. These are lists that we've also uploaded into ARChIE. We'll do we'll follow that up with adding the authorization and restrictions lists. Then we'll expand our results based on structural similarity. And then we'll tag on the substance of very high concern candidate list at the end. So we'll run that. It'll rip through it. So thankfully we saw nothing on the Stockholm and Rotterdam Convention. That makes life easy, but we did find 27 on the authorization restrictions list. We found another 50 that are like the authorization restrictions list. And then we found another 25 that are in the candidate list. But some of these do overlap with the authorization restrictions with the structural similarity expansion here. So we'll look at the results here. And then we will be presented with this list of about 82 substances ranked in order of what will probably be more concerning. So you'll instantly see there's a lot of red associated with this list. That's because when a substance is found to be in a list that we've classified as high hazard, we display the links as red just to alert the users that we'll probably want to focus a bit more on these lists. And yeah, that'll give you the full lists. And if you want to analyze it further, you can always export your results to CSV or Excel and further analyze them. So that'll wrap up the demonstrations. So let's just recap on the follow. So we demonstrated ARChIE. So let's recap on the popular functionalities that are basically from feedback from our users that have managed to try this out. So the first feature that people like to use is that it's highly searchable and it covers the global inventory. So it's very useful for our regulators to have a bird's eye view of the whole global chemical regulation. So that's been quite important, this global inventory feature. There's also the ability to have authoritative data. So being able to evaluate each information you see and seeing if you do consider it as official and its reliability has been quite critical to a lot of our non-scientific end users. They love to be able to be prompted to see if things are is reliable. There's also the ability to search and sort and prioritize based on regulatory context. So the idea of breaking things down and only searching our Australian inventory, for instance, and be able to compare that to our inventories across the world and find these overlaps and differences has been quite critical feature as well. So that's all done by that prioritization tool. There's also standardization. So the data being imported into a common database is a good way of standardizing our data and not scattering it across multiple different files in Excel spreadsheets. So it's been an important feature in standardization, but it also increases transparency with respect to the data that we do have on hand. Linking back to the original source is quite important. So ARChIE just really holds aggregated data. It's not meant to hold every piece of information about a substance. The information that we do hold, the aggregated and high-level information, is tethered with links that will trace back to the original source. So if users are more interested in developing and more interested in looking at this further, then they can go back and click the link and look at the original source. Another feature that's been quite possible is, since this is based on like a web page type of format, every screen that you saw when I did the demonstration is attached to a URL or a link. So rather than sharing results, our prioritization results by using Word reports or PDFs and spending hours preparing these, we can just simply send people a link and they'll be seeing exactly what you're seeing and how you got there. And if they're interested in further, they could always rerun it in the future as the information is updated gradually. So right now it's showing a lot of what I consider low-level functions of ARChIE that have been put together to do prioritization. Where we're going with ARChIE is building it to do something a bit more sophisticated. And the process of informed chemical substitution is something I consider a higher level task that's built on it's going to be built on a lot of the low-level functionalities. So for informed chemical substitution, when you're trying to substitute out a hazardous substance for something that's safer or a safer alternative, it's really a problem that's actually several prioritization schemes put in sequence. So to illustrate that, the first thing that you'll enter into, like such, so you'll be interested in, you'll have a chemical name, a CASA, and all the substance IDs of the chemical that you find concerning that you want to substitute. So the next process is you'll want to do a selection process. So you want to screen through all the substances that are on the that you have information available, and you want to select any potential safer alternatives. So you'll be looking at functional use, so things that have the functional use that you want to apply these substitutes to. Are there any already known substitutes, or is anything structurally similar to these substitutes that you also want to put on your radar? But there's also a screening thing. So this will produce a lot of potential candidates doing this first step, but you also want to cross-check it against anything that are very hazardous. So you don't want to substitute a hazardous substance with another hazardous substance. So you want to be able to have a method of flagging things that are known to be bad substitutes. Are they already on high hazard list? That's a red flag that you want to get rid of potential candidates. Are they associated with PBT properties? That's bad. But also, if we lack information about a substance, we also want to expand our criteria based on structural similarity, just so we capture anything that we've missed, and we're not putting bad substances forward just because we have no information. We can infer this information based on the other bad substitutes that we've flagged. But then there's also a ranking process. So at ARChIE, we have a filter scoring method that allows us to rank our results. So we'd want to start promoting substitutes that we find more promising. So we might consider high import and manufacturing volumes as an indicator of availability. So we might want to promote our results based on that. If they've been assessed as being low hazard already, that's a bonus. So we want to promote those up. Do they have the same functional use and article use category? Have they already been found to be in these categories that you're interested in applying these substitutes to? So this is another way of looking for a good alternative. And at the end of the day, you'll be left with a ranked list of potential safer alternatives, which you will then proceed to assess further and start putting them forward. So I'm going to start wrapping it up and go about the outlook. So I've shown the informed chemical substitution as a goal that we're working towards. But the way ARChIE has evolved, so keep in mind that most of this started about March last year. We only really had what we considered a minimum viable product in October last year. And since then, we've started to follow two different paths of development. So the first path is just developing more features and functionality at the demand of end users. So if we have a particular a section that wants a particular functionality, I'll just put the functionality in. But the other stream is also things that is required by not our end users, but our IT. So making sure that ARChIE is ready to be deployed, can it be sustained in a deployment in a production type of environment? Can the development be maintained long term, and can we release it publicly? And these are the other more boring aspects of ARChIE right now that need to be addressed a bit further, but that's like proper testing, the information security, all the technical documentation and whatnot is still a work in progress. So we're getting to it, but these features are generally working parallel. So I'm going to wrap it up. So most of ARChIE has been written by myself, but I have been very fortunate to get Veronica on board recently. She's actually one of our risk assessors that happens to have a computer science degree. She's been very great in reducing my workload for the last few months, and very talented programmer as well, with a very good background of why we're doing this. The other side, it's been done closely with Glen Walker and Angela. That provided me with a lot of background government experience. I'm very fresh into government, so being able to to constantly ask them about, develop new features. Is it good? Is it suitable for government? They've always been there to answer the questions very immediately, but also provide great feedback and how to develop this further. There's also Sarah Stone. Sarah is our one in charge of the informed chemical substitution. Her work has really set the bar of where ARChIE has to go. So when I develop ARChIE, I always keep these very challenging use cases in mind, just to make sure that I don't develop things with a limitation. I need to make sure when I develop things, is it going to meet these future very ambitious challenges? So Sarah's been kind of the one to really set the bar and what I have to meet in terms of that. And yes, I'll wrap up there. Thank you.
Great. Wow, fantastic. As always, I'm blown away by your work in ARChIE, and I'm glad we had a chance to have this webinar so that other people can see what a fantastic tool you've developed, Daniel, and Glenn, and the others you mentioned on your last slide, Veronica and Sarah. And I think, yeah, and also like a lot of work that you're doing within ARChIE overlaps with a lot of work that we're trying to do in ZeroPM, and such as tackling the global chemical inventory, informed chemical substitution. This is all things that we're working on. So really glad to have this collaboration. And now we're going to open the question and answer period. So feel free to ask any questions there. I see one question there already. And so this is a question about, says, nice tool, thanks, is from an anonymous attendee. What would be considered similar chemical structures? So maybe you can go maybe a little bit into this RD kit, and I saw you had a similarity score of 0.7. Maybe you can break that down, what that means.
Yeah, so the way chemicals are, to do a similarity search, you really have to, we say, vectorize the substance. So when you take a chemical structure, you have to convert it into something of a number. And that's part of the fingerprinting algorithm. So what you saw is RDKit. Embedded in the RDKit library is a fingerprinting method that finds all the features of a substance. And this is a very arbitrary thing. A lot of fingerprinting methods will decide, what features they decide to weight. So it could be a hydroxyl groups, it could be benzene rings. It'll find all these features in a substance and it'll apply a number to it or a vector. So that's the fingerprinting algorithm. So what's considered similar really depends on that fingerprinting algorithm. If it's RDKit, there's also a Morgan fingerprint that I have in there, an Adam Pears fingerprint, another one I don't generally use, a Max fingerprint. These will pick up on different areas of the structure. So the similarity score should be treated, you should scrutinize that, and some similarity methods will be more useful for some purposes and some groups of substances, whereas others could be useful for others. So yeah, so that's just the fingerprinting method. Then we have the Tanimoto score. So once you vectorize a substance, you will also have to work out a way of finding a distance between them. So this scoring method is the way of computing distance. So that number, that has an important impact on the number as well. So yeah, so to answer the question, what would be considered a similar chemicals? That really depends on the chemical itself and the way it was fingerprinted. But yeah, it's always a debatable subject.
No, great. Thanks. That was a good answer. And I mean, and you also mentioned that you're also thinking of substructure as well as a possible way to look at similarity. And that question, by the way, was from Sarah Kazarzon. She didn't mean to be, or he or she didn't mean to be anonymous. Okay. So the next question from Kate Schufield: is there scope for the tool to be used to support assessment of UVCB substances with complex variable and/or partially unknown composition? Yes, well, that's a large part of the inventory that you're looking at.
Well, the answer is yes. The way ARChIE's the way that I've put the tables together, so I've got all the structures in a single table, and the reason I've done that is so you can associate any number of structures to a given substance. So this was done with the UVCB substances in mind, that to capture these substances and analyze them, you're going to have to associate many different structures to the same substance. So I've given a lot of flexibility in the way that can be done in ARChIE. So the way you'd analyze those is you'll be relying a lot on the Cheminformatics side. So you'll be having to do structural searches to flag. Let's just say you've got a particular substance that is like a small part of UVCB. The way to detect that you would do a direct search on the structure, and based on that structure's presence or association with a particular substance, it'll be flagged on there. So that's the way UVCBs are going to be handled most likely going forward. But yeah, it's been a hard one to develop because we don't really have that much information on UVCBs. So I'm hoping to refine the way ARChIE does that as time goes by, but the pieces are there for it to handle it.
Great. And I can say this is also something we discuss a lot in ZeroPM, so we should definitely maybe have some chats about this at some point.
Yes, no, we'll be looking very closely at what you come up with UVCBs, because that information will be very useful.
Great. Next question, Nikiforos Alexakis. Thank you for the nice presentation. Indeed, very informative and useful. How do you perform merging of compounds in a single list? This is not a trivial procedure.
Merging of, I'm not sure exactly what that means. As in like combining two lists into one?
That is how I see it, but maybe there could be more details.
Okay, yeah, so that actually wouldn't be too hard actually. So the way you would do that is you'll go to that prioritization tool and you will do two or searches basically. So you'll say I want anything on this list or something on the other list, and then you'll search that in the navigator, and that will pull them all together. And what you'll do is you just export that all those substances to CSV. And if you want to use that as a new list, you can upload that into our listing tool, which would extract all those identifiers that you've just made, and then you'll make a fresh list that's the sum of the other lists, and that will automatically get rid of any duplicate substances as well in that process. So yeah, you're giving a list with just the unique substances that are on both of the lists.
Mm-hmm. Indeed, yeah. And did you develop your own unique identifiers for this, or did you use existing identifiers?
Yeah, so the substance IDs that are referred to in ARChIE are really arbitrary. So they're just basically there for indexing purposes. And now if someone else spins up an ARChIE system on their computer, they'll have a different ordering system that'll be responsible for assigning the substance IDs. But what gives these substances meaning is within those substance IDs are directly attached to CAS-RNs, EC numbers, chemical names, and it's through those associations that we map substances back to the substance ID. The whole reason why I refer to substance IDs is when we do this mapping process, it can be quite computationally intensive. So when we run things through the listing tool, it'll map that for you once and keep those results in a format that can be rapidly screened as we're browsing substances. So it's easy to quickly check a list, a pool of substance IDs, rather than having to scan the list file that we uploaded and make that connection on the fly. So it's mainly for performance reasons that we do it this way.
Mm-hmm. Oh, and yes, so that makes sense. And I also give a shout out to a similar tool we're using for this in ZeroPM called the Cleanventory, which people can Google if they look into our project. Very cool. And I'm surprised I don't see any more questions on here. We still have time for a few more questions, but I'm surprised nobody asked this one. How can people outside the Australian government use ARChIE, or will that ever be a possibility?
That is something we're working toward. Actually, I think Glenn wanted to answer this one.
Yeah, so look, it is our intent. We're moving in that direction, but unfortunately, well, a byproduct of Daniel's exceptional productivity is that we're a bit behind on this side of the implementation strategy. But because we work in government, there are a series of steps we have to go through that we hope will allow us to publish this open source at some time in the future. But given our current priorities, that won't that won't be before the end of the year.
Okay. Okay. Well, end of the year sounds amazing. That's I would say. I was thinking it'd be like longer than that.
Oh, it could be, but that's our ambitious goal
Okay.
at the moment.
No, that makes sense. No, and when you say it's an open source, so it'll be would it be available as a website like you have now, or that would require hosting and stuff? So it'd be more like you'd share the underlying code and stuff.
Yeah. So ARChIE is quite, I'd say, intensive, and for hosting it for public use would be very expensive for us. And not sure exactly if we'd have. It's not just the infrastructure that's required, but also the amount of work that would be required to administrate such a system. But our goal is to open source it, and with enough instructions, you'll be able to quickly put together your own inventories using your own local system. So ARChIE can be installed on a laptop locally. It doesn't have to be run on a web server. So when it comes out, you'll have the option of making your own ARChIE system and using it for analysis that way. But the extraction tools that we have are quite fast. So it doesn't take long to assemble it. What you saw today in my, I'd say, demonstration set of data, that has over 3 million points of data, and it took less than a day to compile with these extraction tools. So having to do this yourself isn't a hard job.
Oh wow. But still, it is such a powerful tool, and it's definitely something that I see, as I said, I think will be the future and very useful for informed chemical substitution and many other practical values, and I also to what you said, to prioritize for assessment, because this is the only way to deal with the increasing number of chemicals on the global chemical inventory. And if that, I see we are nearing the end of our time, and I see no further questions. And so with that, I would like to say thank you very much, Glen Walker and Daniel Weber, for an excellent webinar and demonstration of ARChIE, the future of cheminformatics and regulation. And I want to thank you all for watching.
Thank you, Hans-Peter. It's been a pleasure.
Yeah, thank you, Hans, and ZeroPM.
Thank you.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.